Hello, everyone. My name is Xiaolong Ma. I am a PhD student from the Department of Electrical and Computer Engineering at Northeastern University. I will present our paper towards the real-time DNN execution with block-based reweighted pruning in this slide. Nowadays, the machine learning is becoming increasingly popular. The deep neural network have emerged as the fundamental element in machine learning application due to its high accuracy and excellent scalability. Many new applications such as self-driving, resolution upscaling, and speech recognition are highly relying on DNNs. To promote the portability and flexibility, more applications are now targeted on the resource-limited device, such as the mobile phones. However, deploying the DNN model on such device is very challenging. First, the huge model size guarantees the good performance for the DNN models, but it is very challenging to fit for our mobile devices. Taking this figure as an example, for speech recognition task, the DS2 performs better than DS1, but it is 8 times larger than DS1. Other networks for different tasks, such as the convolution neural network, transformer architecture, BERT, GPT-3 models, are all consuming very large storage. Besides the storage, a deep and large model usually requires a large computation resources. It increases both training time and the inference time. For example, by use 8 NVIDIA V100 GPU, it will take at least a week to train a BERT model. And even we can use more resources to train a deep neural model in a shorter time. The cost of the power consumption is still huge. For example, during the training of the AlphaGo, it will cost up to $3,000 electric bill per game. And for mobile devices with limited battery, such huge computation, even just for inference phase, will make the battery drains very quickly. Many approaches of DNN model compression and acceleration have been proposed to solve the issues. From the algorithm level, one of the most innovative techniques is the DNN model pruning. It can result in a significant reduction in computation after a large portion of weights are pruned. From the framework level, there are also several end-to-end DNN acceleration frameworks targeting mobile platforms. For example, TVM, TensorFlow Lite, and the Alibaba MNN, but they do not support the sparse computation on the devices. There are two main kinds of weight pruning methods, the non-structured and the structured pruning. Non-structured pruning can achieve a high model compression rate and good accuracy. However, the irregular indices of the compressed weight representation cause the complex workload on the highly parallel architectures. For compiler-level implementation, irregular weight distribution within kernels requires heavy control flow instructions, which hurts the instruction-level parallelism. Also, kernels in different filters have divergent workload, which harms the thread-level parallelism when the filters are processed through the multi-threading. On the other hand, structure pruning exploits the filter pruning and the channel pruning. The compressed model is more regular. It does not require extra indices to store the weights. However, it usually results in relatively low accuracy compared to the non-structured pruning. Static regularization is first utilized in solving non-structured pruning problem by incorporating the L1 regularization into the DNN training. By extending the L1 regularization into group lasso form, structured pruning on DNN models can also be achieved. With specific regularization dimensions, it can perform different types of structured pruning. However, this method yields limited compression rates and non-negligible accuracy degradation due to the intrinsically heuristic and non-optimized approach. Dynamic regularization methods such as the ADMM pruning usually reforms the pruning problem into raw optimization problem with dynamically updated regularization term bounded by the designated constraint sets. During training, ADMM can separately and iteratively solve the pruning problem. Although this method is revolutionary in its functionality and outperforms the former ones in terms of the pruning rate and accuracy, a satisfactory solution cannot always be guaranteed for the non-convex problem. Not to mention that this method suffers from a time-consuming training process. From the pruning scheme aspect, The current structure pruning scheme suffers from the major information loss. The accuracy drop is especially significant in RNN pruning. The motivation of our study is to seek an approach to maintain the regularity in the pruned model while restoring the flexibility of the spatial distribution of the weights. In our proposed block-based pruning, which is applicable for both CNN and RNNs, we take a unique step towards this goal by introducing a new pruning perspective and avoid the pitfall of making this approach a mere trade-off between model accuracy and the regularity. We consider the weight matrix in each layer to be composed of multiple weight blocks with the same size. We apply independent row and column pruning on each block, with the potential different pruning rates in each block to ensure high flexibility. The remaining weights in each block still form a full matrix with a smaller size. Within our perspective, the aforementioned non-structured pruning and the state-of-the-art structured pruning are two extremes in our design with the block size one by one and the size of the whole matrix. From the regularization aspect, we emphasize that both current static and dynamic regularization methods are limited by their intrinsic shortcomings. Towards training the DNN, we minimize the loss function of the network to increase accuracy. In order to achieve structure sparsity, the common method is to add group lasso regularization to the loss function. In fact, achieving block-based row and column sparsity is also a special group lasso problem. It is difficult to find high-quality solution using this fixed regularization method. Instead, an effective dynamic regularization method dealing with such soft constraints is in need. To achieve this goal, we propose to use the Reweighted method to solve group lasso regularization, thereby eliminating the previous shortcoming of applying same penalty on important and less significant weights. We formulate the following two optimization problems for block-based row pruning and column pruning. The P is the collection of the penalty weights, which is updated in every iteration to help increase the degree of the sparsity beyond the group lasso regularization. Please note that the two problems can be solved separately or simultaneously using the standard solver. To get the real acceleration, we use the compiler code generation technique to bridge the gap. What we do is to extract and use the known pattern distribution to do the computation optimization and generate the execution code that can be directly run on the devices. With the unique spatial property of the block-based sparsity, we propose a novel matrix reorder technique to maximize the performance. At first glance, the block-based sparsity has a disordered weight distribution, which incurs significant thread divergence and load imbalance if rows are processed by different threads. As the remaining weights that appears in certain rows and columns in each block have a certain degree of regularity, we first reorder the rows by arranging the ones with the same or similar pattern together. Next, we compact the weights in the column direction. At last, the rows with the same or similar computation are grouped together. As a result, each group is processed by all threads in parallel, and each thread is in charge of multiple consecutive rows. Thus, the computation divergence among these threads is significantly reduced. On the other hand, since the weight distribution pattern in each block is regular and known after grouping, the input matrix that corresponds to each weight group will be loaded only once. The load imbalance can also be relieved thanks to the register level load redundancy elimination. In this slide, I will show the accuracy result of the pruned model with our proposed methods. We can see that in CFAR or ImageNet dataset, our method can achieve significantly higher accuracy compared with both non-structured sparsity and the structured sparsity. Our method with pure structured sparsity, which is named the one block results in the table, can also beat other structures sparse model, indicating the superior pruning method of the reweighted regularization method. We also test the proposed pruning method with the NLP task using the timid datasets. We can see that our results achieve better performance. It indicating that the reweighted regularization method with block-based sparsity can also be suitable for 2D weight matrix. Now we show our on-device inference speed result in this slide. We compared our method with different acceleration framework. They are TVM, TensorFlow Lite, and Alibaba MNN. We can see that our method outperformed baseline results significantly. Based on the results, we can see that our method achieved real-time execution on all representative DNN models. Thank you very much.